Imagine any machine or place, like a blender or a forest. That's a system. An energy system is just a way for scientists to track the energy flowing into, through, and out of that machine or place. We look at what energy goes in, the input, how it changes forms or objects as it moves along, the transfer and transformation, and what finally comes out, the output. Energy is never still. It's constantly flowing from place to place or changing its identity. Think of a system as a machine, anything from a simple light bulb to a complex ecosystem. An energy system is just a way for scientists to track the energy flowing into, through, and out of that machine or place. We look at what energy goes in, the input, how it changes forms or objects as it moves along, the transfer and transformation, and what finally comes out, the output. Energy is never still. It's constantly flowing from place to place or changing its identity. Since energy is invisible, we can't just watch it move. That's why we need to use models. A model is a tool, like a diagram, flowchart, or even a physical representation that simplifies a complicated process. By creating a visual model, we can trace the invisible flow of energy. Models are crucial because they help us understand the process better and even make predictions about how the energy will behave if we change something in the system. When tracking energy, there are two key terms to use correctly: transfer and transformation. Transfer means the energy moves from one object to another, like the heat energy moving from a hot stove burner to a cold pot. Transformation means the energy changes its form within the same object, like the electrical energy inside a light bulb changing its identity to become light energy and heat energy. Both of these processes happen constantly in an energy system as energy moves from input to output. Heat energy can move through the process of conduction. This happens when energy is transferred through direct contact, usually in solids. Imagine placing a metal spoon in a bowl of hot soup. The particles in the hot end of the spoon start vibrating faster, and by physically bumping into their neighbors, they pass that vibration, or heat energy, down the spoon. Our model for conduction simply shows faster moving particles sharing their energy with slower moving ones. The second heat transfer model is convection, which only happens in fluids, gases, or liquids. Think about boiling water in a pot. The water at the bottom gets hot, expands, becomes less dense, and rises. The cooler, heavier water at the top sinks to replace it. This creates a circular current that moves the heat throughout the pot. When we model convection, we use arrows to draw this circular motion, showing how the fluid itself acts as the energy conveyor. Finally, heat can move through radiation. This is energy transfer via waves, like light or infrared waves. Radiation is unique because it doesn't need any physical contact or medium to travel. It can go through empty space. The perfect model is the sun heating the earth. Our model for radiation shows waves leaving the heat source and traveling outward through space to warm the object that absorbs them. A roller coaster is a fantastic system for modeling energy transformation. As the car is slowly pulled up the first hill, mechanical energy is put in, converting to stored potential energy, PE. At the peak, our model shows maximum PE. The second the car plunges down the hill, the stored PE is transformed into kinetic energy, KE. The model shows the amount of PE going down exactly as the amount of KE goes up. When we want to model how much energy is useful versus how much is wasted, we use a Sankey diagram. These models use wide arrows to represent large amounts of energy and narrow arrows for small amounts. When the input energy transforms, the arrow splits into different outputs. The beauty of the Sankey diagram is that the width of the arrow immediately gives you a visual comparison of which output form receives the most energy. Let's use a Sankey diagram to model the energy efficiency of an old-fashioned light bulb. You start with 100% electrical energy input. When that energy transforms, the arrow splits into two. You'll see a tiny, narrow arrow for light, the useful energy. Maybe just 5%. But the other arrow, representing heat energy, will be huge and thick, showing the 95% of energy that was transformed into a wasted form. The model instantly shows how inefficient the system is. The most important system in nature is the food chain, which models the flow of chemical energy. The system starts with the sun's light energy. Producers, plants, are the only ones that can transform that light into chemical energy, sugar. The energy is then transferred when consumers eat the plants. Our food chain model uses simple arrows between the organisms to show the path of this crucial energy flow. When modeling the food chain, you have to account for energy loss. A critical part of the model is showing that only about 10% of energy is transferred to the next level. Why? Because the organism used the other 90% of the energy just to live, to move, to breathe, and to stay warm, transforming it into heat, which is then lost to the environment. Our model, often shown as a pyramid, gets skinnier at the top because less and less energy remains. A simple electrical circuit is a great system to model. The battery is the source of chemical energy. When you close the switch, the chemical energy is transferred into electrical energy that flows through the wires. When the electrical energy hits the bulb, it is transformed into light and heat energy. A basic circuit diagram is a perfect model for describing this series of energy transformations and transfers. Sometimes, a simple conceptual or physical model is the most effective. Think of a line of standing dominoes. This system models a sequential energy transfer. When you push the first domino, you introduce kinetic energy. That energy is instantly transferred from the first domino to the second, and so on. The model shows that the energy itself isn't changing form. It's simply moving from one object to the next in a sequence. We can use a bar graph to model how energy changes in a system over time. Imagine tracking the stored chemical energy in a battery as it powers a toy. We take readings every 10 minutes. Our bar graph would start with a tall bar, showing maximum energy. As the toy runs, that stored energy is used up, so the bars get progressively shorter. The graph clearly models the depletion, or removal, of energy from the battery system. To model the warming of a room, we have to define the system boundaries, the walls and air inside. The heater is the input source, adding thermal energy primarily through radiation and convection. But heat is also lost. Our model must show output arrows where thermal energy escapes through the windows and walls. Conduction. This model shows a dynamic system where energy is constantly entering and leaving. A car engine is complex, but its energy flow can be modeled simply. The chemical energy in the fuel is the input. This is transformed into thermal energy when the fuel explodes. The expanding thermal energy then pushes a piston, which is transformed into kinetic energy that moves the car. A complete model must also include the unwanted outputs, energy constantly lost to the environment as heat and sound. Energy systems are often defined as open or closed. In an open system, like a campfire, energy, heat, is easily exchanged with the outside environment. Heat and light pour out freely. In a closed system, like a well-sealed thermos of hot soup, energy cannot easily enter or leave. While truly perfect closed systems are rare in the real world, this model helps us understand how a system's boundaries affect how quickly energy is lost. Watch a ball bounce. As it falls, it models the PE transforming to KE. When it hits the floor, the KE is transformed into heat and sound, and some is momentarily stored as potential energy in the compressed shape of the ball. Because some of that energy is transferred to the floor as heat and sound, it's lost from the ball's system. That's why the ball can never return to its original height. The energy leaves the system with every bounce. It's important to remember the limitations of our models. To keep things simple, we often ignore tiny energy losses, like the squeak of a wheel or the friction of air. These simplifications make the model easier to understand, but they mean the model doesn't represent the exact amount of energy. Models are designed to help us understand the idea of energy flow, not the precise calculations.